So this is the first of 12 lectures by Rob Kirby on triangulations of topological manifolds. And today he asked me if I'd been to his lectures in Cambridge in 1970 on the same subject. And I said no, but I can catch up now. So that's good. I have various people to thank. Firstly, the parents of Des Shayam, who very kindly bought us the camera which we are using. It's a very nice gift. And then there's the LMS. The lectures are sponsored by the London Mathematical Society Scheme 2 grant. And of course, Rob, who can talk now. You don't need any introduction, I think.
Good. Good. But I need chalk.
Chalk is there.
So, so Andrew did not say that in 1970, when I started speaking at Cambridge on the same topic, that I had come on a visit, and Raymond Licorice, who was sort of my host there, said, just not long before I started, he says, Rob, in Cambridge we prepare our lectures. And which he knew already that I think about my lectures, I don't prepare them. And I couldn't do it today because Andrew has kept me busy all day with helping me do one thing or another. So, topological manifolds. So, today I sort of want to give you an outline of what I'm going to cover, but I'd like to start by setting the scene in the early 60s, which is when I started thinking about topological manifolds, and at which point almost nothing was known about topological manifolds. So let me describe the few things that were known in the early 60s. So probably the earliest useful fact about, not about manifolds in general, but just about Rn was, maybe I should say this is about homeomorphisms, and homeomorphisms of Rn. And if you didn't assume differentiability anywhere, if you didn't assume piecewise linearity anywhere, if it was just a homeomorphism of Rn, you could do almost nothing with it, except that there was Alexander's isotopy. So Alexander, probably in the 20s, what's called the Alexander isotopy, says that if you're given the homeomorphism of Rn to Rn, and suppose that H is equal to the identity outside the end ball of unit radius. So it's the identity outside. Then there exists an isotopy H sub t from Rn to Rn with H naught starts out at the identity, starts out as H, and it ends up as the identity, and throughout the isotopy, Ht is equal to the identity outside the end ball. So if you had this strong assumption, after all, assuming it's the identity outside the ball, then you could make it, you could sort of fill in and squeeze and make the identity inside the ball. And the proof is, well, you just write it down. You write down that T of course is running between 0 and 1, usual thing for an isotopy. An isotopy is an arc of homeomorphisms. Homotopy is an arc of functions, continuous functions, and isotopy is an arc of homeomorphisms. So Ht of a point x is just given by, so it's Th of x over t, or the reverse. So when h is 1, I want it to be the identity, which is, okay, so this should be 1 minus t, and this should be 1 minus t. So now when at time 0, that's just 1 h of x, so it's h. At time 1, well, it's not so clear what it is right off, but you have to think a second. When you're, what does this look like at time a half? So you have this homeomorphism, it's fixed outside the identity out here, and it's whatever it is inside. But now at time a half, you multiply by 2, so a point out here gets pushed outside. Now it's not moved at all. because it's the identity out here, and then you just bring it back to where it started. So at time a half, it's the identity on this point. And in fact, time a half, it's going to be the identity outside the ball of radius a half. Well, then as time increases, it's the identity outside a larger and larger, outside a smaller and smaller ball. And then in the limit, it's the identity everywhere outside the origin. Well, then it's the identity at the origin too. So it's very simple. I mean, it just points a little bit of, a calculus student who understands continuity can understand that argument. And that's the Alexander isotopy, and that, as simple as it is, turns out to be quite important. And there's various versions of it. So here's a homework exercise. If h of x minus x, if that is bounded, say by some constant, so in other words, no point in the plane, Rn, moves too much. If it's bounded, then H is isotopic to the identity, and it's the same proof. So I could say this, but I'll leave it. This is a nice exercise to understand. It's the same formula, and the point is that when you push a point way out, it moves by this, at most, this given constant, and then when you pull it back in, it pulls in to something smaller because of the radial structure. So you take this point, you push it way out here, and now it moves by whatever this constant is, but then when you multiply it, make it come back in, this distance is less than that, by obviously. And so that's why by the time you've pushed the point essentially to infinity and brought it back in, it hasn't moved. So you have a limit on the identity. So I've told you how to do the exercise, but that's not so obvious. Why think a bit about it. And there's other versions of this. I mean, but I don't want to get into this too much in this introductory lecture. So that was known. This is known to Alexander. This was probably observed by Ed Cannell. I'm not sure anybody observed that this version was true in the 60s. And otherwise, well, what else was known? It's not quite clear when the definition of a topological manifold actually I'll give you the definition. It's not quite clear when it arose, because after all, manifolds, I mean, it's attributed to Whitney in the 30s as giving the first modern definition of a manifold as something covered by, well, actually, even he defined it as a subset of Euclidean spaces, defined by equations in Euclidean space. So a manifold is given to you as a subset of Euclidean space. And then Whitney himself proved the Whitney embedding theorem, which said you could put a manifold inside any manifold defined abstractly, you could put it into Euclidean space. So there's really no difference between the definitions. But what was that abstract definition that Whitney used? Well, it's the same, probably roughly the same one as we use for topological manifolds. So since that's a topic of my lectures, what is a topological manifold? Let's say an M manifold. M. So what that is, it satisfies three properties. So the first and most important one is that each point P belonging to M has a neighborhood U sub P, homomorphic to Rm, to Euclidean space. It has to be locally Euclidean. Certainly, manifold has to satisfy that. Well, there's two other properties. And so if you think about this, you might think of the following difficulty. You might define something that looks like the real line, except I removed 0. I notice it's erased here. I removed 0 and put in 2 points. So this is the space in what you have to give it a topology. So you give it the topology that what are the open sets? Well, the open sets have a basis which consists of the usual open sets if you're away from this feature, just the usual open sets. But what are the open sets that contain this point? Well, they're the open sets, they're the open intervals as if that point were right there where 0 is. So that's what, those are the open, that's the basis. We're giving a basis for the open sets. And those are the open sets containing this point. In other words, all intervals that contain 0, except instead of 0, it's named that. It's named now, let's say P. And this is Q. And so the same thing for this point, same open sets. And otherwise, it's just the ordinary open sets, open intervals. Well, now you think about the property, think about Hausdorff. Hausdorff says that any two, if you have a space which is Hausdorff, any 2 points are separated by open sets. Well, any open sets that contain, open set that contains P is going to be intersect any open set that contains Q because it's all the rest of this nearby stuff is going to be in both. So this is not Hausdorff. And yet it's locally Euclidean because each point has a neighborhood homomorphic to an open interval. This point because we defined the open intervals as if they contained it. So this is not Hausdorff, and that's bad. We don't want manifolds looking like that. So the second condition is that the M is Hausdorff. And that's there exactly to avoid this example, this kind of example. Then, for the third condition, well, another problem is you could take intervals from 0 to 1 and just glue them together and glue them together. I'm gluing together half open intervals. You don't have to call them 0 to 1, but just gluing together half open intervals like that. Up to the first, including the first uncountable ordinal. I forget the ordinals. Ordinals.
Omega 1.
Yeah, up to omega 1 there. I forget what they're called. So this is called the long line. And it's too long. It's just too long. So we avoid that. And so that's avoided by paracompactness, which is, what do you have to have? Locally finite, the cover has a locally finite subcover. What is it? Whatever the definition is, avoids the long line, and that's what we want to avoid. Now, let me also say that in the presence of 1, these two are also equivalent to metrizable and first countable. So they'll do the same thing. That's another way. So our topological manifolds have metrics, countable base. So that's what a topological manifold is. Now, this definition, well, in the smooth case, all you do is add an extra condition that says that when you have 2 points and they overlap, so you go from one coordinate chart into the manifold and back out using the other coordinate chart. That composition has to be smooth, both ways. So you can just add that if you want it to be differentiable or piecewise linear. So you can add in conditions for that. So this is sort of the basic definition of a manifold, and then you can add in extra features about how these coordinate charts overlap. Okay, so that I don't know when that definition in this form really turned up, nor who was the first to say it. I'm not sure that's known. So then, one couldn't say hardly much of anything interesting about topological manifolds in those days, in general. However, I guess Barry Mazur and Morton Brown proved the first really interesting theorem about this. So this is Mazur and Morton Brown. And they proved what's called the topological Schoenflies theorem. So Schoenflies had shown that in S, so he had shown that that a circle just embedded in S2, that this circle bounds a two-disc, of the disc on both sides. It's almost, it sort of looks like the Jordan curve theorem, but it bounds a disc on both sides. So this embedding of a circle extends to an embedding of the two-dimensional disc. And that's what Schoenflies had proven. And then it was observed to be false by the Alexander Horn sphere if you went to a two-sphere inside a three-sphere. So that was observed. The Alexander Horn sphere was a counterexample to this version of it. But then what they proved was they suppose that you have an embedding of Sn minus 1 into Sn, which, well, actually, let me see it this way. They really said Sn minus from cross minus 1, 1 is embedded. So they gave it a collar, they gave it a thickening. Then Sn minus 1 cross 0 bounds an n ball on both sides. So no matter how wiggly the sphere was embedded in Sn, no matter how wiggly it was, if it had this little sort of trivial topological neighborhood, if it had that, then it bounded a ball. So this was about 1959. It was Mazur's thesis. Actually, what Mazur did, he required that this have a spot in which it was piecewise linear. It had to have a spot, an open set on which this was a nice embedding. Nice in the sense of smooth or linear or something. He needed that. Then Mort Brown proved the general thing, and then the linearity was removed by Marston Morse in a short paper. But that was Mazur's thesis, and right, he went on to be a topologist, and then shortly after became a number theorist. So that sort of gave the subject an initial impetus. Here's something actually non-trivial that we're starting. I'll give Brown's proof on Friday because we need it for later stuff. So that was the topological Schoenflies theorem, and well, there wasn't really very much else known. So at this point, Milnor published in. So there was a conference in 1963, almost 50 years ago, in which he gave a list of what he considered the most important problems in geometric topology. So he gave a list, and yeah, actually it's an interesting list. I don't know if I want to put them all on the board, but one of them was the annulus conjecture. So it was kind of the next question to ask after the Schoenflies theorem. So one of Milnor's problems was the annulus conjecture. And so what's the next most complicated thing you could have? Well, you could have two spheres, a pair of spheres embedded disjointly, and ask if there's an annulus in between. That was the question. So, given two embeddings, let's say F naught, F naught and F1 mapping the spheres, again thickened into Sn embeddings, and they're disjoint. germ that is the region in between homomorphic to the sphere cross I. Is it just the sphere cross I? So you just got these two embeddings, they're wiggly, and they have these collars. And you're allowed to ignore the collar. But anyway, so they want to know if the region in between is just a sphere cross I. That was the obvious conjecture. So that was one of Milnor's problems. I might as well mention, I won't take time to write them all down, but also he asked, do all manifolds have a triangulation? So in other words, is every manifold homomorphic to a simplicial complex which is combinatorial? That's saying, does that have a PL structure? He asked the Hauptvermutung, German for the main question or something. So if you think back to the early days, homology and cohomology and such things were defined using a triangulation. They're defined simplicity, the simplicial complexes. So suppose a topological manifold is homomorphic to two different simplicial complexes. And you then use them to define the homology groups of that manifold. Well, did you get the same answer? They wanted to know if those two triangulations were somehow equivalent, so that when you calculated homology, you knew you got the same answer. In other words, were homology groups invariant of the topological manifold rather than just the simplicial triangulation you put on it? That was the question. That's why they called it. And then later on in the 30s, and they did simplicial homology, singular homology, and they didn't need that, the Hauptvermutung anymore, but it was still there as a question. So two of Milnor's problems are, do topological manifolds, do the triangulations exist, and are they unique? That was two more. Another problem was, and I won't say any more about it now, but there are triangulations which they didn't know whether there were triangulations of a manifold which were not combinatorial. And the kind of thing which might not be combinatorial is suppose you take a homology three-sphere, for example. So we know lots of examples of homology three-spheres which are not simply connected. So they're not three-sphere. So take this homology three-sphere. It's a simplicial complex because it's triangulated. And now take the suspension. Well, I use a suspending, so it's still triangulated. And now that suspension has now got fundamental group that's trivial. So that's a homotopy sphere, but it's not a manifold at those cone points because a link of that cone point is the homology sphere and it's not simply connected. Whereas in a triangulation, you're supposed to have a nice sphere as the link rather than a homology sphere as the link. So you take that and you suspend again. You doubly suspend. Now, they didn't know. That could have been, when you suspend that time, that could still be a manifold. And if it were a manifold, it would be a homotopy sphere. And so that was the question. Could that, after you suspend twice, could it now be a manifold? And it was generally believed not to be so, but Bob Edwards proved that it was around 1974. So that settled another one of Milnor's problems, just about triangulation. So there's those strange triangulations. So strictly speaking, when you talk about a triangulation, you have to say combinatorial triangulation, because those are the nice ones. A manifold is something which is locally nice. It's locally homomorphic to Rn. Well, a triangulation should be locally nice in that the triangulation should be piecewise linearly the same as a triangulation, ordinary triangulation of Euclidean space. Whereas the ones that Bob Edwards got, some of the simplices were wild, like a wild arc, or like the Alexander Horde sphere. They were very strange. That's how you looked at it. But if you looked at this as the 5-sphere, then the simplices that you were drawing were very, very wild, very complicated. So a piecewise linear structure always means the combinatorial triangulation. So that's the world we usually work in because it's locally nice. But there are the other things. That's 4 of Milnor's problems. Then there was the topological invariance of rational Poitras classes, and that was done. That's the first problem to be solved by Novikov. Then there was the topological invariance of Whitehead torsion. That follows from the stuff I'm going to tell you about. So that was done then. And Larry Seaman and I, at first there was the Agnes conjecture, and then we settled triangulations and uniqueness and the topological invariance of Whitehead torsion. They all fell into the same technique, so that's what you're going to hear about. And Milner's last problem was, of course, the Poitras conjectures, which Perelman finally got. The 3-dimensional one. The 4-dimensional topological one is Mike Friedman, but the 4-dimensional smooth one is still unknown. So there's something left. But that's the only case left of Milner's 7 problems from 1963. So we do progress in topology. So there's those problems. So now, what are the lectures going to be like? Actually, I have quite a bit of time yet. So the lectures, I'm not sure I'm going to keep to this timetable. So I think in lecture 1, well, we're going to go through Brown's proof.
You don't mean today's, you mean Friday's.
Lecture
3.
3, Friday. 2 is on different topics.
Yeah.
So Brown's proof of the Schoenflies theorem. And I'm not sure when I'm going to get to the torus trick then. And what are called stable manifolds, stable homomorphisms. And well then, the torus trick is going to come perhaps I'll mention it in lecture 3. Yeah, probably I will. But anyway, torus trick. And from that, local contractibility, the space of homeomorphisms of Rn, and then in general an N-manifold. And then, well, let's see how it goes. So somewhere in here we're going to get to well, these have names, but then I have to start explaining what they're about. Well, we're going to go on. In about, I don't know, about lecture 7, well, somewhere in here, lecture 6 or 7, we're going to talk about topological, we're going to get applications of topological transversality, the existence of handle body structures on topological manifolds, topological handle bodies, and things of that sort. What I do is put off having to use surgery theory as long as possible, because then I'm bringing in a big machine. Whereas before, everything in a sense is elementary. You don't have to hardly have any background to understand what's going on in these early lectures. I'm going to try to keep it that way as long as possible. So somewhere in here, somewhere in here we get to triangulations. And as part of this is PL structures on, well, basically on N torus. That's where the surgery comes in, walls, non-simply connected surgery. And we go on from there to finish up But that's the order. So as I say, if you're you do have to be interested in this, but if you are, then it should stay fairly elementary for quite a while. So maybe I should, again, since this is kind of a general lecture, let me state what these theorems are about triangulations, so that you'll know what's coming. So, right, so the statement is that given manifold, I'm not going to do the most general version where the manifold has a boundary. Let's leave that out. So given M closed, closed, oriented, I don't know. Let's make, closed and M greater than 4. Well, not equal to 4. Then M has a PL structure, so that's the nice kind of triangulation, PL structure. What this really means is that each point has a neighborhood homomorphic to an ordinary rectilinear subdivision of Euclidean space, and the neighborhoods overlap, not simplicially, but if you subdivide each one, then they overlap as simplicial. So you always have to subdivide. You always, you might have two triangles overlap this way. Well, then you have to, if you subdivide some, what do you have to do? Put some simplices in, you put some more vertices in here, do a batch more subdividing, and then suddenly they overlap. By simplicity. That's all that. So that's automatically there in the piecewise linear world. You're always subdividing. But so then otherwise the semi-linear, the piecewise linear structure from one chart and from the other chart agree. That's really what's supposed to be true. Just like if you're doing a smooth manifold, you have two smooth charts, then the smooth structure you get in the overlap from either one they have to agree. You have to be able to, doesn't make it, if you're doing calculus in this one, you better get the same answer as if you do calculus in this chart when they overlap. That's all that's means. So then M has a PL structure if an obstruction in the fourth cohomology of M with coefficients of C mod 2 vanishes. So there is an obstruction. And we'll understand that obstruction, why it occurs. It's really, tomorrow I'll mention this, it really has to do, it actually goes all the way back to the Harf invariant, or in this more particular area, Rock-Leans theorem, which says that there's no smooth spin 4 manifold within signature 8, which in some sense should be there, and it isn't there. There's the absence of that. There is one of signature 16, but not 8. The algebra says there should be one of index of signature 8, and it's not there smoothly. It is there topologically, but it isn't there smoothly or piecewise linearly, and it's that missing manifold that causes this obstruction to exist. So I'll sort of explain that at some point. So M has a PL structure. If M has a PL structure, then the PL structures up to isotopy, correspond one-to-one to the third cohomology of M with Z2 coefficients. So if M has a PL structure, then that this is how many it has, it's whatever this group is. And if they have the same invariant here, then you can just move one to the other by an isotopy. Now, I should mention that this theorem had a predecessor due to Dennis Sullivan, and he showed that if you had two PL structures, then up to homotopy, they were given by the image of this map, the Bockstein, into the fourth cohomology of them. So he pushed it forward, and then that classified PL structures up to homotopy. So in other words, the idea here is that you have these two PL manifolds, and it's the same underlying manifold. So you have a homeomorphism between these two PL manifolds, and this means that homeomorphism is isotopic to a PL homeomorphism. This means that homeomorphism is homotopic. Let me write that down. So you replace this with homotopy, and that corresponds to that obstruction. So it's easier to take this homeomorphism and homotop it to a PL homeomorphism than it is to isotop it. And then you can ask, well, you have a homeomorphism between these two PL homeomorphisms. Forget about that homeomorphism. Just ask, are the two PL manifolds PL equivalent? Don't worry about whether that has anything to do with a homeomorphism. That question is just hard to answer. I mean, that's just, I have nothing to say about it. Nobody has anything really to say about it. So we want to get at this. This is m not equal to 4. In dimension 3, the way we prove this can be used to prove it for 3 manifolds as well. This was written up by in a master's thesis at Oxford by A.J. Hamilton. So the old proofs in dimension 3, Moise and Bing and those people that are kind of hard work to prove that 3 manifolds are triangulable, that can be done, I would say, considerably easier, assuming you know this kind of material. It's kind of a corollary that you can do all this in dimension 3. Dimension 2 is just even easier. And then in dimension 4, Mike Friedman, he classified simply connected topological manifolds, and if they have odd intersection form, there's 2, and they're distinguished by this same invariant up here. So one of them, he has these two, in the topological world, given a homotopy type with an odd intersection form, then there can be 2 topological manifolds realizing that homotopy type. One of them can't be triangulated because that invariant is non-zero. The other one, the invariant is 0, but it may or may not be triangulated. But anyway, this crops up in dimension 4 also. Well, then, the question, yeah.
So a random question. I mean, this is very reminiscent to the theorem on the existence of spin structures, where you have the obstruction in H2, and then the spin structures of isomorphism are classified by H1. So the question is there anything in between? I mean, is there anything whose obstruction is in H3 and classified by H2?
Is there anything in between? Nothing I know of. I mean, you can ask for, there's questions about Lipschitz structures, for example. So Dennis Sullivan used some of these ideas, but he replaced the torus trick. He replaced this, this is not really answering your question, but it reminds me of something. The key, this is an N torus that we're talking about here. Right here. It's an N torus, and the 2 features that we want about the N torus are that the universal cover is n space, and that if you remove a point, you can immerse it in n space. So for Lipschitz structures, Dennis Sullivan needed a hyperbolic manifold. So he needed a manifold whose universal cover was hyperbolic in space, and also that if you removed a point, you could immerse it. And that was very hard to construct, and it was hard work for him to do that. And then he could use the same techniques to show that every manifold had a Lipschitz structure. So the Lipschitz is weaker than PL and stronger than just being topological. And so so he proved that everything except maybe in dimension 4 had a Lipschitz structure, and then with Simon Donaldson, using Simon Donaldson's method, proved that in dimension 4 some manifolds, if it's not smooth, it doesn't have a Lipschitz structure either. So that's a structure between topological and PL. But that wasn't really a question, which I guess I didn't really understand. But
No, it was a very random question. We didn't
Yeah,
talk about it.
okay. Right, so there's this, and then, let's see, what else might I tell you of a general nature? I could say that, so I could talk about these, I could tell you something, I won't address this later, but there is this question about triangulations, about the non-combinatorial ones. So for example, the 5-sphere has different triangulations. It has a unique piecewise linear structure, but using these other kinds of triangulations, in other words, you take any homology 3-sphere, suspend it twice, and you get the 5-sphere topologically. So that's those have strange triangulations. So it's possible that manifolds where this obstruction exists, and they don't have PL structures, they might yet have a topological, a triangulation of the weak kind. And they do. And so it's actually, so this is work of Belusky and Stern, and Takao Matsumoto. But the net result of that is that everything has a triangulation of some sort, except, well, everything would if we knew. So here's the question: does there exist a homology 3-sphere with Wagner invariant 1? So this will be mentioned in my talk on Wednesday. There's two kinds of homology 3-spheres, and half of them have trivial Rocklian invariant like the 3-sphere, and half of them have Rocklian invariant 1, and an example of that is the Poincare homology sphere, which is a famous homology 3 method. I have Rocklian invariant 1. So does there exist a homology 3-sphere of this kind, such that it's double. If you connect some with itself, some homology 3-sphere H, such that H connects some H bounds it's either acyclic or contractible. There's two different questions. Well, anyway, either one of them is interesting. Bounds on acyclic or manifold. So that's an interesting question. And if it does, I think this is the version, don't quote me on this, I haven't looked it up recently. But if it does, then every manifold, topological manifold, has this weak kind of triangulation.
So, would you just take H cross an interval right now?
Okay, you convinced me that.
So H
I
minus
have
the
the wrong
cross an
version
interval.
of the contraction. That'd be contractible. Yeah, there's something. Yeah, so it should have said contractible, thanks. No. All right. Well, I've still got maybe 10 minutes. Let me give you a preview. After all, the interesting thing, which is there's a simple idea, there's an interesting thing which makes this all work, and that's called the torus trick. So I'll just give you a preview, since not all of you are going to come back and listen to this. So what's the idea? Well, let's take the simplest case where we have a homeomorphism. So I'm going to draw a diagram. So I'm going to start at the bottom, and we have a homeomorphism H from Rn to Rn. So this is a homeomorphism. And for this version, I'm going to assume that h of x minus x is small on a compact set. So that means it's close to the identity in the compact open topology. So if you wonder whether two homeomorphisms are close, they're close if they're close on a compact set. If you ask for homeomorphisms to be close on all of Rn, then you find that a rotation is not even continuous, it's not even an isotopy. Because if you think of a rotation, no matter how small the change in the angle, way out at infinity has moved a huge distance. So the right topology on homeomorphisms is what's called the compact open topology, which means essentially that nothing moves very far in compact sets. So suppose that's a condition. I don't mean that. I mean, it's actually less than absolute when it's a compact set, on some compact set. So it's close to the identity. All right, now I'm going to immerse the torus minus a big disk here, and I'm going to immerse, same immersion, but I'm only going to cut out a smaller disk. This one's twice the radius. So this immersion, there's a theorem about this, but I'll just draw the case, which is, you've seen this immersion before. So here's the immersion of a punctured torus, two-dimensional torus. So there's the torus with a pair of handles, but this is actually an immersion, so this is where the double points are right there. So there's an immersion of if you puncture the torus, you take out a disk, then it's one disk and two one handles in dimension 2. And I've taken out the big disk. Now if I took out a smaller one, if I take out a bigger disk, then this will be thinner. So it'll just look thinner, etc. I won't cover the whole picture. So this is the thinner one. So this is the torus, let's call this alpha. So this is alpha of Tn minus the big disk. And this out here, the bigger thing is alpha of Tn minus a smaller disk. Take out something smaller, you get something bigger. All right, well now, if this homeomorphism, so this is all in some compact set C, and I put this inside C. So this is C, our compact set. So this is happening inside there. And so this homeomorphism is as small as I want. Okay, if it's small, then where does it go? Well, it wiggles a little bit, but it stays inside the bigger one. It doesn't move far enough to get outside. So that means that because of that, this homeomorphism lifts to an embedding called H bar. and lifts to an embedding. Just because where does the point go? Well, this point moves, say, over to here, and that lies inside the other image, and since it lies inside the other image, it's in here. Or if the point is here, well, if the point came from this handle and moves a little way, I don't lift it into that handle, I lift it into the same handle. So there's no problem with that. So we get this. Well, then this sits inside the end torus, does this. And I have this embedding. Well, now if you look at the missing disk, so there's this disk, and I want to extend over this disk. Well, this disk is inside anyway, this is just the Schoenflies theorem, because there's a coordinate. I mean, what have we done? We've got the torus here. And what I did was cut out a disk at the top and then immersed. And then I have another one. I've got this embedding, which wiggles something, which has a wiggly guy in here. Well, this wiggly guy sits inside a chart. So this wiggly guy is in Euclidean space, and the Schoenflies theorem of Brown and Mazur says it bounds a disk. So that's how we can extend this embedding to a homeomorphism, which I'll call, I don't know, H double bar. But you extend because it's just how you fill in a disk, and the Schoenflies theorem tells you how to fill in a disk. Now comes the punchline. Now you've got a homeomorphism of the M torus, and it's actually close to the identity. So now take the universal cover, go to Rn, and just this is the universal cover. Let's say H hat. So this is the map. This is the map e to the it's the exponential map. Usual exponential map from the M torus from Rn down to the N torus. What does H hat look like? Well, it's periodic. Because this is the lattice, the integer points and so on. That's how you map from Rn down to the N torus. So each one of these squares maps down around the 2 torus. And so when you lift this, well, where does this square go? Well, you might as well fix a point. You can arrange and fix a point. So this might look like this, so it looks like this everywhere. Periodic. And then maybe this guy goes like that, so then it goes like that everywhere. What does that tell you? That tells you that H hat is bounded. No point moves more than some constant. Remember Ed Canel's theorem, remember that from the beginning. It's bounded because it's the same on every compact set. Well, it's bounded on a compact set. It's got some maximum distance a point is moved on a compact set, but then that's the same for every compact set. So it's bounded. Therefore, H hat is isotopic to the identity. We didn't know anything at all about the original H except it was small. It was small in a compact set, not small everywhere. It was small in a compact set, and this trick converts it into a homeomorphism which is bounded, and therefore isotopic to the identity. Well, how is it related to this original H? Well, you can take a ball down here, which sort of sits down in the zero handle of this torus, and you never have to touch that. So this ball, which sits inside here, is also the same ball inside the torus, and in here, and then when you lift up, it's the same one. So this ball is kind of preserved throughout this. And the same thing, the ball, it's that same ball that sits over here, etc. And so really, these H and H hat agree on some ball or a ball half that size. They agree somewhere. And if they agree somewhere, then if this one's isotopic to the identity, so is this one. So this I don't know how big a deal this looks like, but the important feature about this is that without this, if you have a homomorphism, you simply don't know what to do with it beforehand. You just couldn't get your hands on it. It was merely a homomorphism, and even if it was close to the identity, that didn't help. But now all of a sudden, it's isotopic to the identity. And that turns out to be a big deal. And so then you can cross this, you can have a parameter. Well, first place, you can check that this is all canonical. That if you change H slightly, everything else changes slightly. So not only do you get this isotopic to the identity, but it's isotopic to the identity in a way which varies continuously with H, and so you get local contractibility of the space of homomorphisms of Rn. Well, I'll finish with a comment that this arose, Chernovsky in Russia had written in a preprint with a different proof of local contractibility. This was 1968. I was reading the preprint and puzzling over what he was doing when I realized that if you started with a homomorphism of the torus of this kind, its cover was bounded and therefore isotopic to the identity, which meant that this homomorphism was what was called stable. Well, that was already interesting, but then it got down to here, and then in some ways everything, within 3 months we had all the theorems because everything followed so nicely in this trick. It's called the torus trick, like this. So I'm gonna, on Friday I'll go back through this in more detail, and maybe I'll do it crossing with a K-ball, because it works just as well if you have a K-parameter family of homomorphisms of Rn. Works just as well. And then you've basically done this for handles. If you're done for handles, you can do it for manifolds, and you get local contractibility for manifolds and a bunch of other things. So we're going to prove theorems about topological manifolds using this, and we'll do that for a little while, and then we'll get to triangulations, which uses a different version of this. We don't always want to assume this homomorphism is false, because it's just some homomorphism. Well, then what can you do? And it's a different version of this, but it's closely related. So that's what's coming up. Thank you very much.
Does anybody have any questions?
Yeah, I mean, how big a restriction is this? I mean, if you've got a homomorphism, you can, let's say, take a point, you can isotope it so that the point comes back to where it started, and then it's small enough.
It's small, yeah, but it's always, you can fix a point.
Yeah.
Because you certainly can just translate a point back to where it came from. So you can fix a point, but that's not saying very much, this, you see, you have to think about what it means, what the definition of what the topology is in the space of homomorphism. So two of them are close on a compact set. Well, if the compact set is tiny, you haven't said very much.
Yeah, I guess that's my question.
This has to be tiny on a compact set. It has to be small enough on a compact set so that this is satisfied.
Okay.
That's what it means.
Right.
And
yeah, so C's got to be relatively big compared to that.
Yeah. It has to be big compared to you pick the C first, and then you pick epsilon.
Okay.
To get this how small an open neighborhood it is.
Okay.
Yeah. Yes.
Did you say that when you puncture the torus, you can always find such an embedding?
Such an immersion.
Immersion,
This
sorry.
immersion, yeah. This is, so two comments about that. This follows from Smale's and Hirsch's, but really Smale's immersion theory, which is a beautiful, I mean, I think it's the arguments that Smale has in that work more remarkable than his H-cobordism theorem, which is what he got the Fields Medal for. But that's just my opinion. But this is quite remarkable because his theorem about immersions, remember it said that you could turn the two-sphere inside out in 3 space, which everybody thought was impossible. So he was proving something that was really surprising. H-cobordism theorem wasn't surprising. It was almost in the air. So that's a theorem that you can do this. But then Milnor, upon hearing of this work, actually constructed these immersions. A couple of other people did too, but Milnor's construction is an appendix in the book that Larry Siebenman and I wrote. Lots of this is joint. I mean, this isn't, but lots of this is joint with Larry Siebenman. Yeah, almost everything from now on is joint with him. But Atiyah has an appendix which gives you actually instructs these. Yeah, and I think you can almost see it. You see this picture in the plane. Now for the 3 torus, put an axis here and you spin this plane around, and that crosses these handles with a circle. So that's an immersion, and then you have to work with the 2 handles of the 3 torus. The 3 handle of the 3 torus you don't have to worry about. That's the point you take out. But you have to do the other handle. So there's some more work. But I think that's what, if I remember right, what Atiyah does. So there's both a construction and a general theorem. This immersion theory that Smale started, it went through versions for the different categories, PL. There's a version with submersions, there's a number of versions of it, including the topological one. And then Gromov, in his thesis in about 1969, generalized it to what were called microjibkis, some Russian
Flexible.
word.
Very flexible.
Very flexible. And then he has a book called the H Principle, something or other on the H
Partial
Principle.
differential relations.
Partial differential of the H. And that's still more generalizations of the idea behind Smale's thing for immersions. I mean, it's basically getting an embedding or something out of homotopy theory. If the homotopy theory is right, then you get this kind of thing. Well, that was just taken a huge way by Gromov.
Yeah.
Yeah.
See on your picture you've drawn there of the arms intersecting, and then if you move the point slightly on one arm, you can. What did you say?
You can lift it. You see, you want to define this and that.
Mm-hmm.
So if you have a point here on an arm, it moves just a little bit, then you take it to the same arm over here, move just a little bit. You don't take it to the other arm. That's all you have to do in deciding how to lift.
Okay.
See, when points overlap, then you have to choose one of them to get an embedding here.
And what if it moves onto like the point where the arms cross?
Well, it shouldn't. If you have a point, if you have a point out here that happens to go here, it just stays on this arm.
Okay.
It's as though that arm didn't exist when you're lifting. You just keep it on the arm. You keep it on the arm it began on.
What does that look like in terms of like visualizing it? Like
Well,
the way the arms cross, is it?
If you think of the torus drawn that way,
Yeah.
you think of it drawn that way, then you're thinking of it as, let me draw this picture then. So there's the bottom of the torus, and then you have a one handle that goes up and over and is attached. And then you have another one that goes, well, you can even attach it up here. Well, better here, I guess. And you have another one that goes way over to here.
Okay. I see.
And now this just moves a little bit. So if you have a smaller one, and it just moves a little bit, then it's still inside the bigger one, and that's where it goes.
Okay.
So yeah, that's easier to see in that picture.
Thanks.
Yeah.
Okay, thank you. So the next lecture will be on Wednesday at 3:30 in lecture room C, downstairs. Okay,
3:30, not 3.
C. Lecture room C.
3:30, not 3.
Oh, 3:30, I'm sorry. Yes, thank you very much.
It is 3:30?
It is 3:30.
Okay.
Yes, it is. I meant 3:30.
You said 3:30,
Yeah, it is 3:30. Definitely 3:30, followed by Michael Attia at 5. Okay, thank you very much.